This is Unit 2, Lesson 7, Part 1, Velocity and Other Rates of Change. This isn't necessarily covered in the AP Calc curriculum at this point, but it is covered quite a bit, and it's covered very quickly later on, but it is a big part of the AP test, and this is interpreting the meaning of a derivative in context. So we started with related rates, and then we started talking about instantaneous rate of change. And then what we notice is that now we're going to apply our derivative rules to some straight line motion, which many of you are familiar with from physics. Now, we do have two different types of notation, and one was a friend, so to speak, of Newton. His name is Lagrange, and he came up with our F prime notation. And Leibniz, as I've said before, is a German mathematician that used the dy dx. Sometimes it's easier for application problems to use dy dx because we're talking about functions, and they usually have different names like the position function, the velocity function, the acceleration function. So it just depends on the situation. So we'll go through this then. Okay, so example 1 says, suppose that s equals f of t gives the distance of feet of an object from a fixed point as a function of time in seconds. So what is the common term for ds dt? Well, that would be our velocity, our change in position over time. So that's like feet over seconds, or feet per second, miles per hour. That is our velocity. So the notation ds dt at t equals 4 would be the velocity of the object at 4 seconds. And part C says, what is the real meaning of f prime 4 equal 18? And so what we're saying is, since the position function is f, the derivative is going to be the velocity. So it's just a different way to write ds dt. So this is the velocity giving us a specific value. The velocity of an object at 4 seconds is 18 feet per second. Okay, so next, let's go to the moon. So Neil Armstrong would have picked up a rock and thrown it at a velocity of 24 meters per second, or 86 kilometers per hour. The height of the moon rock can be modeled by the function s of t equals 24t minus 0.8 t squared meters per second, because the gravity force on the moon is different than the gravity force on Earth. Find the velocity and acceleration of the moon rock as a function of time. So just a little note there, the acceleration will be the acceleration of gravity on the moon. So and again, it's going to be different than it is on the Earth. So we're going to find the first derivative, s prime of t is going to be 24 minus 1.6 t. And then s double prime of t, which will be our acceleration, is going to be negative 1.6 meters per second squared. And that's the gravity of the moon. That's the gravity constant for the moon. Okay, how long will it take the rock to reach its maximum height? So we are going to take this equation, it's quadratic, and we're going to have to find the vertex. So we're going to use our negative b over 2a. So our t is going to be negative b, which will be negative 24, over 2 times our a, which is negative 0.8. And when you simplify that, I'm going to get the negatives, I'll get 12 over 0.8. And when you divide that out, you get 15 seconds. So it takes 15 seconds to get to its full height. So how high did the rock go and when did it hit the ground? So for its height, we're just going to substitute our 15 seconds into our original equation and get the value. And this will be 360 minus 1.8. So we get 358.2 meters. And when did it hit the ground? So what you want to do is set the equation equal to 0 and solve it. And this is going to equal 0. And then you're going to solve this for t. So I'm running out of space here. So t times 24 minus 0.8 t equals 0. So obviously it's on the ground at t equals 0. And when you solve this equation, you get t equals 30 seconds till it hits the ground. Okay, so something other than motion, because that was just we've done these in pre-calc. Most of you have had physics, you do them in physics. So there's the other things where we have rates of change, such as rainfall, temperatures of different things. I put yams in there, volume of a cone, how quickly people get infected by viruses, all kinds of things where we look at rates and how they affect different quantities. So that's where the derivative helps us at a specific moment in time. So the next example, suppose W of x is the daily quantity of water in gallons required by a palm tree of height x feet. Explain the meaning of each expression in a complete sentence, including units. So here we have the original function. Our x is now replaced with 25, and that is the height of the tree, and the value of the function is the quantity of water. So we would write that a 25-foot palm tree requires 38 gallons of water each day. So in the next part, we're looking at the inverse. So we want to talk about this in the opposite direction. So we would say when a tree is 25 feet tall, it needs 38 gallons of water each day. And then for part C, we have the derivative. So we're talking about the rate of change at 25 feet. So a 25-foot palm tree tree's daily quantity of water increases at a rate of 6 gallons per foot. Okay, so we can use rates for any kind of change. It is acceptable to just say rate of change instead of instantaneous rate of change, but other times you have to make that distinction depending on how you're describing something. So the next example describes that. Suppose C of T represents the cost in dollars per day to air condition your Florida beach house when the temperature outside is T degrees Fahrenheit. So we want to explain the meaning of C prime of 90 equal to 0.37 in a complete sentence, just like we did before. So before I do that, I just want to write over here that our C function is degrees Fahrenheit per dollars a day, and our C prime is dollars per day per degree. Okay? So when we write C prime of 90 equals 0.37. What we're saying is when the temperature outside well, that was a weird way to spell outside. That looks funny. When the temperature outside is 90 degrees Fahrenheit, the air conditioning costs are increasing, and since this is a derivative, it's going to be a rate, by 37 cents per day. Okay, and then part B, approximate the cost of air conditioning in your beach house when the temperature is 94 degrees Fahrenheit, given that C of 90 is 2.64 and C prime of 90 is 0.37. Show your work that leads to your answer. So the C prime of 90 equal to 0.37 is what we said in part A. It's that the cost is going to increase when you're at 90 degrees at 37 cents per day. And C of 90 is giving us the cost of the air conditioning when it's 90 degrees outside. So it would cost $2.64. So let's just write a couple things down here, starting with that the 0.037 is the rate. Want to remember that's the rate to air condition your house for temperatures, we're going to say for this part, between 90 and 94 degrees, even though that's a big change, 4 degrees, but for the conditions we're given, that's what we're going to have to work with. Okay, so we're going to make an approximate average rate of change here. So we're going to say C of 94 minus C of 90 over 94 minus 90. This is approximately equal to that 0.37. Okay, so because that's a rate, and so we're using a difference quotient formula for that. So we don't know what C of 94 is. That's what this part is asking us to find. How much, when our temperature is 94, is it going to cost us? So we know what C of 90 is. We were given that. It's $2.64. And then our change in temperature is 4 degrees. And again, that's approximately equal to 0.37. So if you were to multiply this by 4 and then add the 0.37 to that, you would get your answer. So we're going to have an answer that the cost at 94 degrees is approximately equal to $4.12 per day. And I'm going to stop here with this video, and I will continue with the next topic on the next video.